Pick up a titanium watch, a medical implant, a component pulled from a commercial aircraft. Each one feels different from ordinary metal, lighter than you expect, stronger than it looks, and when you check the price, significantly more expensive than almost anything else made of a single material. Now consider this: titanium is not rare. It is the 9th most abundant element in the Earth's crust, more common than copper, more common than zinc, more common than lead. It is sitting in the ground under every continent on the planet. So why does it cost so much? The answer is not about how little of it exists. It is about what the element does the moment anyone tries to extract it. Let's get into it right here on Small Things. The metal that fights back. At its core, titanium is not simply a strong, light metal. It is a material that nature has gone out of its way to lock away. Every other common industrial metal can be extracted using the same ancient technique. Heat it up, add carbon, let the carbon pull the oxygen away, collect the metal. Iron has been made that way for 3,000 years. Titanium refuses it entirely. Add carbon, and it does not release the oxygen cleanly. Instead, it grabs the carbon too, forming a brittle compound no engineer would go near. Every standard method produces something broken. Every obvious shortcut fails. The metal sitting in enormous quantities beneath every continent is, by chemistry, one of the most difficult substances on Earth to actually hold in your hand. Not rare, not hidden, just locked. 100 years of trying. It did not start as an engineering problem. It started as a mystery. In 1791, a British clergyman named William Gregor was examining black sand near a stream in Cornwall when he found an oxide he could not identify. He published his findings quietly. Nobody paid much attention. 4 years later, a German chemist named Martin Heinrich Klaproth independently confirmed the discovery and gave it a name. He called it titanium, after the Titans of Greek mythology, the beings of immovable, unyielding strength. It was a fitting name. The element would spend the next 150 years resisting every attempt to tame it. By the 1880s, 2 Swedish scientists had managed to produce a sample that was roughly 94% pure. In 1910, an American chemist named Matthew Hunter produced titanium that was almost completely pure, working out of a General Electric laboratory. His method used sodium as a reducing agent. It worked but was dangerous and expensive to operate at scale. Pure titanium existed, it just could not be made in any quantity that mattered. As late as 1945, there was essentially no commercial production of titanium anywhere in the world. A metal more common than copper, known for over 150 years, still lived only in small laboratory amounts. One engineer of the period famously described titanium as a streetwalker because it would pick up anything and everything, bonding with oxygen, nitrogen, carbon, whatever surrounded it the moment conditions allowed. The breakthrough came from William Kroll, a scientist from Luxembourg who had been working on the problem since 1930, initially in his own home laboratory. He developed a method that first converted the ore into a liquid, then used magnesium inside a sealed vacuum environment to strip away the chemical bonds holding the metal captive. Oxygen and nitrogen could not reach the reaction. The result was usable titanium. It was slow and expensive, but it worked. By the early 1950s, serious quantities of titanium were being produced for the first time. The Cold War had arrived, and aircraft needed to fly faster and higher than steel or aluminum could survive. The United States military poured resources into scaling up the process immediately. The method Kroll developed in his home laboratory is still the dominant method for producing titanium worldwide today. More than 80 years later, nobody has found anything cheaper. Why the ore does not matter. So why does an abundant ore produce an expensive metal? Think of it less like mining and more like a hostage negotiation. The titanium is in the ground, but it is bonded to oxygen with a grip so strong that the standard tools of extractive chemistry cannot break it without producing a different useless compound. The Kroll process works around this by first converting the ore into a volatile liquid called titanium tetrachloride. Through chemical reactions at over 1,000 degrees, the titanium is persuaded to bond with chlorine instead of oxygen. Then, inside a sealed reactor from which all air has been removed, magnesium is introduced. The magnesium strips the chlorine away and leaves behind pure titanium. What comes out the other end is not a bar of shining metal. It is a gray, porous, crumbling mass called titanium sponge. It looks nothing like the material in a luxury watch or an aircraft fuselage. It looks like something recovered from a demolition site. From there, it must be melted, sometimes twice, inside vacuum furnaces specifically designed to prevent any surrounding oxygen or nitrogen from entering the metal during the process. Even a trace of either makes the final product brittle. Here is the detail that explains the cost more clearly than any other single fact. The entire process runs in batches, not continuously, and a single 10-ton batch of sponge requires 90 hours of vacuum separation alone, followed by cooling, mechanical separation, and quality inspection before anything moves to the melting stage. Steel runs continuously, day and night, in enormous industrial volumes. Titanium is made slowly, carefully, one sealed reactor at a time. The ore may be common. The process of freeing the metal from it is anything but. The problem has not been solved. The assumption most people carry about expensive industrial materials is that the price will fall, that researchers will find a better method, and within a generation the cost will come down in line with everything else. That assumption has not held for titanium. Researchers have been trying to find a cheaper extraction route since the 1950s. Several alternatives have been developed and seriously tested. The FFC Cambridge process, developed in the 1990s, uses electrolysis to pull titanium directly from its oxide and shows genuine promise for reducing energy consumption. But as of today, none of these alternatives produces commercial volumes of titanium for less cost than the Kroll process. Decades of determined effort have not replaced it. The machining problem compounds everything. Once you have a piece of titanium metal, shaping it into a finished part is its own separate fight. Titanium conducts heat poorly, which means when a cutting tool moves through it, the heat builds up at the cutting edge instead of spreading harmlessly through the material. Tools wear out quickly. Machining speeds must be kept slow. A block of titanium that enters a machine shop as raw stock may leave as a finished component representing less than half the original material by weight. The rest becomes chips and shavings on the factory floor. And because every gram of that waste carried the full cost of extraction, smelting, and refinement, it is among the most expensive metal waste generated in any industry. Now the world pays for it. Today, you will find titanium wherever the combination of strength, lightness, and corrosion resistance matters enough that cost becomes secondary to performance. In aerospace, the Boeing 787 Dreamliner contains around 15% titanium by weight. The SR-71 Blackbird, the fastest piloted jet ever built, was constructed from more than 90% titanium because at the speeds and temperatures it was designed for, no other available material could survive. The metal did not dominate aviation because it was affordable. It dominated because nothing else performs the same way. In medicine, titanium is the material of choice for implants that must function inside a human body for decades without causing a reaction. Hip replacements, dental implants, spinal rods. It is the only common structural metal the human immune system does not recognize as a foreign object. Bone grows directly against it. No other widely available metal achieves this at comparable cost. In every product you encounter made from titanium, you are paying for every step in the chain behind it. The ore, the chlorination reactions, the magnesium reduction, the sponge, the vacuum furnaces, the slow, careful machining, the waste that came off the block. What you hold is the output of a process that fought the elements' chemistry at every single stage. The cost of common things. So why is titanium so expensive if so much of it exists? Because abundance in the ground means nothing if chemistry locks it away. Iron is common and cheap because carbon and heat can pull it free in hours, at industrial scale, continuously. Titanium is common and expensive because nature bound it so tightly to oxygen that the only viable extraction method takes days per batch, must run inside a sealed vacuum environment, and has not been meaningfully improved in more than 80 years. The price of a titanium implant or an aircraft part is not a reflection of scarcity. It is a reflection of how much energy, time, chemical engineering, and precision machining stand between the ground and the finished object. Titanium is not expensive because the Earth barely has it. It is expensive because nature locks it away, and every useful piece of titanium is the result of a long fight against chemistry. If this changed the way you think about something you have seen in a jeweler's window or on the wing of an aircraft, let us know in the comments what everyday object you want us to look at next. We might make it our next episode. Thanks for watching. History often hides in the smallest details.